Hi everybody, Dave here. So I have in front of me the new Renogy Pro 3 kilowatt sine wave inverter, and we're going to do some tests and take a look at the inside and see what it looks like. This is a sponsored video and Renogy sent this inverter to me, so let's open it up and see what's inside. First glance, my initial impressions, this is a pretty clean PCB and the process looks pretty good. So this is the output stage. You have some IGBTs here with their own heatsink. On the input side we have some DC fuses. These are like the small car fuses. There are 14, so that's something like 5 kilowatts of potential surge that you could get through these fuses without blowing them. Obviously on the input of the inverter we do need to have a fuse. These are just a last line of defense. They definitely did not just copy and paste this design from somebody else. This is pretty unique, and I've looked inside of a lot of inverters, even off camera, and I haven't seen one look exactly like this. This is your GFCI outlet. Here are the terminals for hardwiring it into your load center. We've got a ground and a hot and a neutral. Did they wire the live and neutral and ground terminals correctly? I find that on many inverters you would be shocked. They're wired incorrectly. And it's something you need to be aware of. So I'm going to go ahead and check that. Good news is they didn't get the wires backwards. I also checked if the ground and neutral were bonded out of the box on this inverter, and they are indeed. Now just to explain a little bit about how this inverter works. We have these cables here, and there's several of them bundled up for current sharing, and you actually have some switching components that are hidden down in these heat sinks, and these are connecting alternately back and forth, probably to ground, and that current flows through here and magnetizes this transformer. There's these copper wires, and those are the windings on the high side, so this creates high voltage AC from low voltage DC. I don't know what frequency they switch at. It's pretty high frequency, but anyway, you end up with high voltage AC coming out of this coil here, and that is rectified using a rectifier, and then the high voltage DC that comes out is put in a capacitor, which is then switched through these components here to create the actual sine wave output at 120 volts AC. Other components that you'll find on boards like these are filters, so they actually run the AC output through filtering, and that's pretty important. Bus bars right there instead of wires, so that's nice. I like to see that. This is actually more expensive, I think, than doing it with wires. And you can see those little boards that are sticking up at right angle. Those actually control the inverter. They look very nice. Well done. I like this design and layout. Here is the inverter's control board. This has a microcontroller along with its crystal oscillator. Anyway, the build quality on this inverter looks fairly good. It has a very clean PCB design. Appears to even have the designer's name right there, unless I'm misinterpreting that text. Everything is glued down, including these capacitors. The transformer there is glued down, which is good because this thing is heavy, and if you drop the inverter or shake it, it could actually break off the circuit board. Quite ironically, I did drop this inverter. It landed on this tab here, and you can see how the paint is bubbled up there. And this whole tab here was actually bent, so I bent it back. But it did not affect the operation of the inverter, and none of the components came loose from the board. Cooling design, one dedicated fan for the output switching, 2 more fans for the hot air to come out the back of the case. I know a lot of people complain about fan noise, and I get that. I like peace and quiet. I don't know how loud this inverter will be, but it's just something I will keep track of and mention as part of the review. In some of my prior videos, I have modified the fans on my inverters to make them very, very quiet, but I don't know if I'll be modifying this particular inverter. We'll see. Enough looking at the nerdy stuff. Let's take this thing out and stick some cables on it and make it work. DC and AC solar room, 2 of my charge controllers. There's 2 separate solar arrays feeding them. This is my 55 volts DC off-grid system, no charge controller, no inverter. I'll link all those videos in the description. These are all 12 volt batteries. And we have 4 aught or 0000 gauge cables that are feeding the Renogy inverter itself. And just a small suggestion for Renogy. The bolts that were included with the terminals on the inverter were too short. These are M8 bolts. You can see how I put longer bolts in so that the proper amount of thread can engage from the bolt down to the nut. Otherwise you'll get a high resistance connection and that bolt could strip out when you're not watching and you could actually have a failure. They don't quite fit M8 bolts right through. They actually have an interference fit and they tend to thread the battery terminals. So what I recommend is find a way to drill them out a tiny bit so that the bolt goes right through and into the nut. Be careful because these bus bars or terminals are actually soldered straight onto the circuit board, and be careful when torquing the bolts to support the terminal, as that plastic part could crack and it could also break off the circuit board. I'm not going to give this inverter a thumbs down for the bolts. Things like this are standard DIY tasks, and not everything is perfect, and that's reality. But I just wanted to warn my viewers to be careful if you use this inverter. Take care of the terminals and don't place torque forces on them that are unnecessary. If the worst thing I find about this inverter is the bolts, we're doing good. I've got my oscilloscope monitoring the sine wave, and we're running a 12,000 BTU window air conditioner. We're now pulling almost 118 amps on the 12 volt DC side. I've also plugged in a toaster oven. This inverter is approximately 1/2 loaded and it has a good sine wave output. I don't see much distortion, if any. It has not yet turned on its fans. I don't know when it will. I guess we'll see. The fan you're hearing is from my charge controller, not the inverter itself. The inverter has been running the toaster oven as well as the 12,000 BTU air conditioner for quite a while now, about 1,500 watts roughly, and I have not heard the fans at all. It's just a little bit warm. So I have two commercial vacuum cleaners that I'm going to switch on using this power strip, and I'm going to watch the sine wave on my scope and we're going to see how it behaves. So the inverter's fans did come on for a little while when it was running around 2,000 watts. 12,000 BTU air conditioner plus a 1,000 watt toaster oven plus two commercial vacuum cleaners being switched on. Let's see what happens. Well, actually, that was pretty good. The sine wave is remaining stable, even under a 1,000 watt inductive load being turned on at the end of a long extension cord. Yeah, this thing doesn't have any problem delivering a surge to an inductive load. At around $450, I expect this inverter to perform well, and so far it does. One of the things I notice about it that's really good is the standby idle power draw is around 8 to 9 watts. Sometimes it hits 10 watts. That's pretty good. Many inverters in the 3 kilowatt range are going to be much higher than that. They're usually more like 20 to 25 watts. I decided to really push the inverter in a different way. I've got both commercial vacuum cleaners plugged in addition to a space heater, which is right here. I'm going to go ahead and have that turned on low, and it's going to have to start the two vacuum cleaners along with the space heater. This space heater has a little bit of a kick when it first turns on, and so this is really going to be a punishing test. Let's see what happens. This is probably going to be pretty hard for the inverter to do. 12,000 BTU air conditioner running about 560 on the AC side, about 900 watts for the toaster oven. I've got another watt meter here just for the vacuum cleaners and the space heater. When I turn this switch on, two commercial vacuum cleaners as well as a space heater on high are going to be turned on. 1,782 watts plus 714 plus 934. Well, that was a pretty impressive test, so let's try it again and make sure it's not just a random chance. So that was over 3,500 watts on the AC side, and it did not beep, it did not make protests, it did not shut down. The sine wave did not deviate, and I must say that this inverter has impressed me. It's not falling over. That's really good. So Renogy did a good job here. I'm a little bit suspicious of that test, so I just want to run it again to make sure that I didn't get a good result by chance. 655 watts on the air conditioner, 920 on the oven, and now let's turn on the 1,800 watt load that's on the end of this extension cord. Just so you know, this test was not staged. I didn't really know for sure this inverter would be able to run those two vacuum cleaners and the space heater plus everything else without falling over. I'm always skeptical of inverter efficiency claims. If you can get into the 90% range, you're good. The efficiency on this inverter came out to right around 92.5% under a 1,000 watt load. It's what they state in the specifications, and I have no problem with that. Based on my experience with other inverters, I've tested quite a lot of them. This inverter is pretty much behaving like a Mack truck. It's able to do more than its rated output. It does not complain, it doesn't beep, it doesn't shut down. 3,500 watts is not a problem for this inverter. I just wouldn't run it like that all day. So I'm impressed that it can do that. Sine wave stability was at the top of the chart on this inverter compared to other machines that I've tested. Many of them exhibit severe distortion when you push them really hard. It depends. And the sine wave stays nice and round even when you're pushing the inverter extremely hard. This is kind of an unreasonable test, but I'm going to push it even harder. And let's see what happens. This is a 200 to 250 watt PTC space heater. We have our toaster oven as well as our air conditioner running at 680 watts. To be honest, I don't think it's going to necessarily pass this test. I mean, I don't really need it to. You know, let's really push this thing super hard and see what it can do. I'm used to seeing high-frequency inverters fall over all the time. Usually when you get near their rated wattage, they start to collapse. This inverter doesn't do that, and I must say it's genuinely impressive. So I pulled 2 kilowatts of AC through this connection here because I added this heater. That was 2 space heaters and 2 commercial vacuum cleaners. Then I had the toaster oven, which is over 900 watts, and the AC, which was 680 to 750 watts. This inverter did not display any harmonic distortion on the sine wave, and it continued to run all those loads. There was no alarm code, there was no beeping, nothing. It just keeps running. So this inverter is able to overload for a period of time, and it shrugs it off. It doesn't care. I don't know how long I could get away with that. In my case, I just want to see, can it be overloaded and does it behave gracefully? The inductive kick that comes on with those vacuum cleaners is very, very high. So I really don't need to see any more. I can recommend it. Now, what I don't know, what I can't tell you is what is the longevity of this inverter? Is it going to last 3 years, 5 years, 10 years? I don't know. That's one of my main concerns, and I do have to mention it. If you like this video and you want to support my work, please thumbs up, comment, and subscribe. Thanks for watching, folks, and I'll see you next time.